Hello, junior geologist. We are going to study geology, and we're going to study from this book called Prehistoric Life, the Definitive Visual History of Life on Earth. And the publisher is Dorling Kindersley, and it's written by a lot of different scientists who put their names and their studies in this book so that we can learn from them. And what we are going to start on this, oh, look, the very first page has trilobites. Trilobites are my favorite. They've been around. They were on the planet about 525 million years ago. And what we are going to learn as we go through this book, we will start off with the young Earth, life on Earth, and then the rise of the humans. So this is a long book. It's a big book. So we're going to have a lot of geology to study in this book. And there's all different topics under each subject that we're going to look at. So when we first start, we're going to talk about the young Earth. After the Earth's formation, do you know how old the Earth is? The Earth is older than your grandparents. It's older than the ground you're standing on. It's older than the oldest person you know. The Earth is very, very old. It is 4.56 billion years old. And over this 4.5 billion years, a lot of geological events and processes transformed it into a planet that is able to have us be able to live on it. Because at first, there was no oxygen. People couldn't live on a planet 4.6 billion years ago. So we will explore the Earth's past. We will look at the origin of the Earth, the first 500 million years, which a lot happened in that 500 million years. And then we'll start on plate tectonics, and then we'll go through a lot of other subjects. And this is the title page, Young Earth, the title page for this section, and it is Young Earth. This is a beautiful book, as you will see. There are all these pictures of all these things and things that we're going to talk about, and I will probably be able to focus in on pictures as I talk about these things. More than 200 years of science has gone into figuring out how the Earth formed and how the rocks formed and everything in its 4.5 billion year history. Geological time has been measured and divided. So like the week is divided into days: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Geologic time is divided into eras and eons and periods, and those periods and eons and eras can be millions of years old. Really long time, because it takes a long time to build a rock. But every year there are new discoveries in geology and new ways to figure out geology, and there's so much geology on the planet that hasn't been done yet, because it's a pretty young science, which means, well, it's only been around 200 years. Chemistry is a lot older. What other sciences? There's engineering things that are a lot older. Geology is just a young science at only 200 years old. The processes, and a process is a turn of events. So a lot of events go together to make a process. And the processes that made the Earth over 4 billion years ago have left its records in the rocks. So we can look at rocks, geologists can look at rocks and analyze them and study them and figure out how old the rock is, how it was put down, how the sand and the dust and the metals and how everything came together to create that rock. And we can see those things in these rock layers. So geologists take these rock layers and we can look at those and find fossils and minerals and metals and crystals and things that tell us how old those rocks are. In the 18th century, which is in the 1700s, a geologist, he was a naturalist and a farmer actually, but he was also the father of geology because he looked at some rocks and said, wonder how those got there. Because there's some that are going up and down, vertical, and there are some that are going side to side, which is horizontal. So these rocks going up and down and these rocks going side to side, he looked at those and thought, boy, that just doesn't look like it happened really quickly. That looks like a huge thing happened and then another huge thing happened, and he was right. And it took millions of years, and there's gaps in the record. So as the rocks are forming, sometimes there are sections that are missing that we can't tell what happened in that section of time. So since he saw missing parts of the geologic record, he decided that Earth had a very interesting history and not like what they had been teaching up to that point. And he realized that there had been episodes of mountain building and erosion. So mountain building is when the mountains build up. Erosion is when the mountains wear away. The Rocky Mountains that we see where the Tetons are, that you can see out your window, or some of us can see out our windows, this is the third set of mountains in that same spot. Because the others have grown up into big tall mountains, and then it gets eroded away with wind and water and freezing and thawing and all of the things that can make rocks wear away and turn into little tiny rocks and turn into sand, and then it all gets washed down to the ocean. Different types of evidence tell us that Earth has a layered structure. Where are we? There we are. Earth has this layered structure. There's an inner core, an outer core, the mantle, and then the crust. And the inner core is really hot iron and nickel, and it's solid. And then the outer core is liquid, and they're both really, really hot, but the inner core is solid because it's so much pressure and so much heat. Everything is all compacted together to make the inside of the planet. And the mantle is the next part, and it's made of dense rock, and it's almost completely solid, but it still can flow like a liquid. It's kind of like really warm plastic. Like if you leave a plastic bottle or a plastic bowl or something on or near the stove and it starts melting, it's still solid, but it can move a little bit. So that's what the mantle, that's the texture of the mantle. And then there's the crust, and the crust is what you're standing on. The crust is the hard part, and the water is all, like the oceans and lakes are also on top of the crust. So they're all part of the crust. And the crust has igneous, metamorphic, and sedimentary rocks, and we'll get into those. Most rocks, rocks are put into igneous, metamorphic, and sedimentary, like I said. Igneous rocks are volcanic rocks. So igneous rocks are rocks that have already been melted by a volcano or magma, or a volcano, they didn't have to actually erupt to be magma and to be igneous rocks. They could be liquid underground and cool off while they're underground, and then they get pushed up and the ground gets eroded away, and we are left with all these beautiful granites, like this pink and black and white one right there. I bet you have granite where you are. And then we have metamorphic rock, and metamorphic rocks can become metamorphic from heat and pressure, or one or the other, but usually it's heat and pressure. When one way that metamorphic rocks are formed is when hot lava is up against another rock. So if you've got this pool of hot lava, then all of this rock on the outside of it is going to get really, really hot, but it's not going to quite melt. It's going to get just kind of smeary and smushy like this. And that's one way we get metamorphic rocks. Another way is if they're buried really deep and other rocks are sitting down on top of it. Tons and tons and miles of rocks are sitting down on top of it, and they smush it really, really hard, and then it just starts, the rock just gets really smushed, and that's called metamorphic rock. And sedimentary rock, the layers of these rocks, this is sedimentary rock, and these are rocks that are just laid down layer by layer, and then they get lithified, and lithified is just cemented together so that they're all one rock. Sometimes sedimentary rocks aren't layers like that, but a lot of times they are. And sedimentary rocks are also the ones that contain fossils. So if you find a fossil, it's most likely going to be in a sedimentary rock. Sometimes they can be in metamorphic rocks, but a lot of times the metamorphic rocks will ruin the fossils from the heat and the pressure. Okay, we will move into the solar system and how the solar system began. In the beginning of the solar system, about 4.56 billion years ago, the Earth was just part of a big swirling hot disk of gas and rock. Well, it started out as gas, and it was called, this big swirling mass of gas is called a nebula. And it was just this huge, like bigger than the whole planet, bigger than the sky. From where you can see the entire sky, a nebula is bigger than that entire sky. And it's cold, gas, and dust. And the dust and the gas that came from, that formed this solar system, is believed to come from other stars that are much older that have already died and blown up. Just blown up and thrown all their rocks and thrown all their gas and star material like gold and nickel and hydrogen, and all of these things came from other blown up stars. And those pieces all kind of gather together. And as they gather together, they get a little bit more and more compressed. And then they get hotter and hotter. And then the very center gets really, really hot. And as that heat builds and builds, then it can just turn into a sun from the pressure and the heat. And that sun will have swirls and swirls of other gas that gets trapped within the gravity of that sun. And that gas looks like a disk. So this is the proto-solar system. Proto means pre. So this is the pre-solar system. It's just the swirling mass of gases. And the sun, all these gases get hot in the middle, and the sun gets in the middle, ends up in the middle. And then all the gases and everything starts collecting together, and then they start bonding and forming rocks, and then those rocks start clustering together. And as those rocks cluster together, they're still swirling around the sun, and they get bigger and bigger and bigger clusters until you have a planet. Or sometimes the gas gets clustered all together, and it can get bigger and bigger clusters of gas until you have a planet. So you have rocky planets like Mercury, which is the one closest to the sun, Venus, which is next in line, and then Earth, which is the third planet from the sun. And past Earth you have Mars, and after Mars there's what's called an asteroid belt, and these are all just big chunks of rock that never did make it into a planet. And past the asteroid belt you have the gas giants. The inner planets around the solar system are called rocky planets because they're made of rock, like the Earth, made of rocks. And the planets on the outside of the asteroid belt are called gas giants because they're just made of gas, and they're huge. They are way huger than the Earth. many, many times huger than the Earth. And those gas giants are Jupiter, Saturn, Uranus, and Neptune. Jupiter is right now on September 5th in 2020. Jupiter is really bright in the sky, and you can see Jupiter and you can see Saturn. And sometimes the moon will line up, so you have just a line of really cool astral bodies, and they're really pretty. But they get further and further away from the sun so they don't crash into each other. The rocks, so as the smaller Earth is rotating around the sun and clearing the path, so it's banging into all these rocks that are in its way in the solar system as it goes around the sun, and it collects all these rocks. And at one point, this Earth gets smashed by this big chunk of rock, and it's about the size of Mars, so it's a huge planet-sized chunk that slams into the Earth and knocks a huge chunk off. And that huge chunk is still molten lava, and it's swirling around the Earth. And as it swirls around the Earth, it starts to cool off. And as it cools off, it gets collected by a bigger rock called the moon. And the moon has cleared that path around the Earth. So the moon is orbiting the Earth as the Earth is orbiting the sun. And that's how all of the planets had to evolve, is they cleared, this is the Mars-sized planet smacking into the Earth, knocking off a big bunch of lava, and it's swirling around the Earth and getting cooler and cooler. This is like a ring around the Earth, and that ring turns into the moon. I think that's good for today. We're going to stop at that, and next time we will start on the first 500 million years. So we'll talk about the formations of rocks, how the rocks started to form, how the planet cooled off. Maybe we'll talk about magnetic poles. This is really fun. The Aurora borealis comes from the Earth's magnetism, because the Earth is just like a great big magnet. And then we'll talk about life forms starting to form. And before too long, we'll get to trilobites, which are my total favorite. So until next time, happy rock hunting.